Welcome, class. This will be the third lecture on statistics. This is going to be on chapter 3, central tendency. I'm going to pull up my PowerPoint so that all of y'all can follow along with me. Hope y'all are having a great day today. All right. So let's start the show. Current slide. All right, so once again, this is chapter 3, central tendency. And some of the outcomes that you should gain from this lecture and reading this chapter, which I highly advise reading the chapters in the textbook, is to understand the purpose of central tendency and the measure of central tendency, how to compute some of these central tendencies that we're going to go over, how the mean changes when you change and do different things to the scores that make up the mean. And you should understand when it is appropriate or inappropriate to use certain measures of central tendency, and how these measures of central tendency are related to each other. And lastly, how these measures of central tendency are drawn and how to interpret graphs displaying different means and medians representing different treatment conditions or groups. So the tools that you'll need in order to be successful in this particular chapter and the lecture is to have a good grasp and understanding of the summation notation that we discussed for chapter 1, and to have a good grasp of the frequency distributions we discussed in chapter 2. I want to remind everybody, I don't think I've said this in the previous 2 lectures, but in statistics, the way this class unfolds, every chapter kind of builds on the previous chapters. So it's very important to understand the chapters that come before the one you're working on currently. If at any point in time you have any kind of difficulties or issues, do not hesitate to get in contact with me and we can work on it. All right, let's continue. So a good overview. All right, so what is central tendency? What do we mean by that? So a central tendency is a statistical measure. All right, it's going to be a single score that's going to define the center of a distribution. All right, and so what is this purpose? The purpose is going to be essentially to find the best score to represent the distribution or the entire group. All right, the best score. All right. Let's see. So this brings up, well, what do we mean by the center of the distribution? As we learned in the last chapter, the last lecture, not all distributions are symmetrical, right? Some are skewed, and they all don't look like a Gaussian or a normal distribution. So defining center may look different, all right, for different distributions. So for the distribution A, right, if we wanted to know what is the center, what is the number that best represents the distribution, most people would probably say 5. All right, it's in the middle, right, of the distribution. The majority of scores are going to be in the middle as well. So that looks like a good choice, a good option for the center of the distribution. All right, but then we have figure B. All right, and B, it gets kind of a little bit weird, right? Some who are looking at this lecture may go, well, the distribution in the middle, the center, is 5, right? It's right in the middle here between the scores. So that's a good, a good candidate for being the center. Others may go, well, it could also be 8, right? 8 is, is a lot of scores are have a lot of the participants had a score of 8, right? So this looks like it could be a center as well. So that's where it gets kind of fuzzy. And then lastly, we have 3.1c, right? And this is a distribution, right? But defining what is the center, again, this is kind of awkward, kind of weird. Some people might go, well, again, 5 is going to be the middle of this. That's how I would identify the center, right? Some people would say that. Others may go, well, hey, can you have 2 centers? So they may go, it's 2 and 8, all right? And so we're going to talk about the different measures of central tendency that we use, and again, when it's appropriate or inappropriate to use them, and how they change. So again, the central tendency measures. There is no. What I want to kind of point out is there's no single concept of the best central tendency measure. In research science or social science, we kind of use the best central tendency measure for the distribution that we're working with. Because different distribution shapes, they're going to require different conceptualizations of the center. And we're just going to pick the one that works the best. All right. It's not always the same one. All right. So some formula. All right. When we're going to talk about our first measure of central tendency, and that's going to be the mean, or also called the arithmetic average or the arithmetic mean. It's the same, right? So the mean is going to be the sum of all the scores, right, divided by the number of scores in the data. So if we're dealing with a population, all right, they're not going to say, give me the population mean. What they're going to do is they're going to have this symbol right here. And that symbol right here is pronounced mu. It's a Greek symbol, all right? And it means the population mean. And so the population mean is going to be the sum of the X scores divided by the population of scores at capital N, right? And this one here is the sigma, right? So sigma means summation. So the summation of the X scores divided by the population of scores is going to give us the population mean, or mu, right? Now, we're not always dealing with a population. Sometimes we're dealing with a sample. Essentially, most of the time we're dealing with a sample. If they wanted you to find the sample mean, well, the sample mean is going to be symbolized as an italicized capital M. All right, capital M. And the only thing that's going to change in the formula besides the capital M is this right here, right? So that lowercase italicized n means we're dealing with a sample, the sample size for our study, right? So this one is saying, hey, we're going to sum up the X scores and divide by the sample size, all right? And so as a rule of thumb, in statistics, usually Greek letters, when they're in equations, they're going to stand for a population parameter, like we discussed in chapter 1. And if we have English letters, they're going to stand for a sample statistic. All right. So that's usually the way it kind of works. All right. I'm sure most people are familiar with the mean, but I'm going to do a quick calculation. So let's say we have a population of scores. It is 1, 2, and 3, right? If we add all those up, that gives us 6, right? So it's summation of the X scores, right? One person got a score of 1, one person got a score of 2, a third person got a score of 3. We're going to add those up, and then we're going to divide it by the population of scores. So it would be 6 divided by 1, 2, 3, divided by 3, which is going to give us 2. All right. So that's going to give us the population mean. All right. So this is a quick one. We're going to do some more with the mean. All right. So let's look at another example. Right. So this one has, a population of scores. There's 4 of them, 3, 7, 4, and 6. And so we're going to sum up the x scores. 3 plus 7 plus 4 plus 6 gives us 20. And divide by the number of scores in the population, which is 4. So 20 divided by 4 gives us 5. All right, so some alternative definitions for the mean, right? Usually in grade school, we learn mean, in a kind of straightforward definition, but you can look at it in different ways. And some of those different ways are more appropriate for when we learn higher level concepts in statistics. So we can look at the alternative. We can look at the mean as the sum of the scores divided by the number of scores in the data. That's how we normally look at it, right? Or we can look at it as the amount each individual is going to receive when the total is divided equally among all the individuals in the distribution. All right, that's a key one. We're going to go over that particular definition in more detail. And a third definition is going to be, we want to look at the mean as a balance point for the distribution. And that's going to be very important for other statistics that we're going to use in later chapters. So let's give a better example of the second definition. So the second definition has to do with dividing the total equally, right? So the example is given is, hey, a group of 6 boys, right? So we're dealing with a sample size of 6. So 6 boys buy a box of baseball cards at the garage sale, and they discover that the box contains a total of 180 cards. If the boys divide the cards equally among themselves, how many cards will each boy get? All right, so you should recognize this problem represents the standard procedure for computing the mean. Specifically, you have the sum of the scores divided by the sample size to produce 180 divided by 6. So the mean is 30. So each boy is going to receive 30 cards. So the mean defined as dividing the total equally. All right. So in that previous example, it demonstrates that it's possible to find the mean as the amount that each individual gets when the total is distributed equally. All right. So we could take this definition and solve some different kinds of problems, right? So let's say we still have those 6 boys, right? And they decide to sell their baseball cards on eBay, right? If they make an average, so the mean, if they make a sample mean of $5 per boy, right? What is the total amount of money for the whole group, right? So, we don't know exactly how much money each boy has. The new definition of the mean tells you that if they pool their money together and then distribute the total equally, each boy is going to get $5, right? And if there's 6 boys, right, then it must be 6 times 5, which means 30, right? So then that means the sum of the scores is $30, right? So that would satisfy there being 6 boys and each of the boys getting $5. All right, so that's pretty much a very simple algebraic equation, right? where you're essentially you're just solving for the missing uh, x, right? But if you look at it that way, right, you can see how you could do different kinds of things with the mean. All right. So the third definition was looking at the mean as a balance point, right? So this kind of alternative definition is going to, describes the mean as a balance point, right? So consider we have a population consisting of 5 scores. So we have a population of 5 scores, 1, 2, 6, 6, and 10, right? So the population, right? Uh, the total of those scores, right, is 25, right? And if we were calculating a population mean, this mu symbol is right here. It'd be 25 divided by 5, which gives us 5, right? Now, if we show this population drawn as a histogram, right, with each score presented as a box, right? And if we presented it in a way that is sitting on a seesaw, right? If the seesaw is positioned so that it pivots at a point equal to the mean, then it will be balanced and will rest level, right? Everyone's been on a seesaw before, hopefully. So when it's balanced, it kind of it doesn't go too far up, too far down. It kind of stays stable, right? The reason that the seesaw is balanced over the mean is going to become clear when we measure the distance, right? The distance. This is going to be a very important part. We measure the distance of each score from the mean, right? So again, the mean was 5, right? Let's take each score and see how far away the mean is, or how far the score is from the mean. So one of the scores is 1, right? So this is 4 points below the mean. We have a score of 2, right? That score is 3 points below the mean, right? Then we have a score of 6, 2 scores of 6, each are 1 point below the mean, right? Because the mean is 5. And then we have x equals 10, and that is 5 points below the mean, right? So now the mean is going to balance the distances. That is, the distance below the mean is the same as the total distance above the mean. So if you add up all the scores, right, that are below the mean, well, that gives you 7 points, 4 plus 3. If you add up all the scores, so 6, 6, and 10, right, that are above the mean, well, that gives you a score, a total points of 7. So the mean is a balance point between all the scores above it and all the scores below it. All right. So let's look at this in a more concrete kind of way. So those are those same numbers, right? But represented in, remember, this is a modified block histogram, right? On a balance, on a seesaw, right? And this is the mean, the population mean. So we have 1 score of 1, 1 score of 2. 2 people scored a 6, and 1 person scored a 10. And now we're dealing with the mean as a balance point based off distance from the mean, right? So these 2 scores are fairly close to the mean. This score is further away, and these 2 scores are further away. The mean is a balance point between those scores that are, as far as distance is concerned, lower than the mean, and those scores, as far as distance is concerned, above the mean, as we outlined in the previous slide. All right. So let's do some learning checks. I want to make sure that we kind of are getting the gist of this. All right. So a sample of 12 scores, right? So we have a sample, right? That's a lowercase italicized n. So we have 12, our sample size is 12, and it has a mean, a sample mean, denoted by an italicized uppercase M, has a sample mean of 8. What is the value of the sum of the scores? So we're kind of working backwards, right? So the idea to think about this is, hey, if we have 12 people and we give each people 8, right? That is going to give us our sum of scores, right? So that is essentially multiplication. So 12 times 8 gives us 96. All right, so we're kind of just working backwards if you think about it. I mean, you could solve it as an algebraic equation, right? If you really wanted to, all right? But, you know, I don't think that's necessary, but you could, right? If it was an algebraic equation, it would look something like this. X over what? 12 equals 8, right? So X over 12 equals 8. Remember, to get rid of, you want to isolate the X, right? So you would multiply this by 12 over 1 to get rid of the 12. And whatever you do to one side, you're going to do to the other side, right? So this would be 12 times 8. And that would give you 96 equals X. All right. So it's a simple algebraic equation. What I'm trying to stress to you, because this will be very helpful in later chapters, is to think of the mean along the lines of those two definitions that we previously went over. So here's the answer. All right, so some characteristics of the mean, right? So think about the mean as a balance point, right? If we change the value of a score, it's going to change the mean. All right, and I'm going to show you examples of all these. I'm going to go over with some of these different characteristics. Another one is if we introduce a new score, right? Or if we remove a score, it's going to change the mean. Unless, this is a very big caveat, unless the score added or removed is exactly equal to the mean. If it's the same score as the mean, nothing really changes. All right, so additionally, if we add or subtract a constant from each score, it's going to change the mean by that same constant. Now, what do we mean by a constant? A constant means that we're going to do the same thing to each of the scores, right? So if I say we're going to multiply by a constant of 2 all the scores in our distribution, that means we're going to multiply all the scores in our distribution by that particular constant. If I say we're dividing all the scores by a constant of 3, that means we're dividing all the scores by 3. If I say we're adding 19 to each score in our distribution, well, that constant is, you know, the addition of 19 to each score in our mean. All right. So if we add or subtract a constant from each of our scores, it's going to change the mean by that same constant. All right. If we're multiplying or dividing each score by a constant, we're just going to, the new mean is going to be multiplied or divided by that same constant. All right, so this will make a lot more sense when we do some examples. So let's look at some examples of this. All right, so the example of changing the value of a score changes the mean, right? So right here I have 3 scores, 1, 2, and 3. We add those up, gives us 6. 6 divided by 3 gives us 2. Let's say I change a number, right? So instead of a 1, I now have a 7. It's 7 plus 2 plus 3. That gives us 12. 12 divided by 3 gives us 4. So now we have a new mean if we change the value of a score. All right. Another one is if we introduced a new score, right, or remove a score. So let's say I still have the 3 scores, 1, 2, and 3. So that equals the mean of 2, right? But now I introduce a new score. All right. So if I introduce a new score, that is going to change the mean, right? So I had 1, 2, and 3, but now I added a 6. So now the sum of the scores equals 12, and the mean is now 3, which is different from 2. So the mean has changed. However, I told you there was a caveat, all right? If we introduced a new score, right, or remove the score that was exactly equal to the mean, well, the mean is going to stay the same. So let's look at an example. I'm still going to keep with the 1, 2, and 3 as my population of scores. So we still have that mean of 2. Let's say I added an additional 2 to my population of scores. So now I have 4, a population size of 4 scores, and one of the scores is equal to the mean, right? Well, if I add a score that's equal to the mean is going to stay the same, all right? And so this one stresses the idea that the mean is a balance point. Before I move on, let's go back to that seesaw, right? If the seesaw is a balance point, right? This is the balance point. If I were to add a 5 right here, right? The 5 is on the balance point. If we're on a seesaw, it's right in the middle, it's balanced. So there won't be a change to the balance of this particular seesaw. Even if I added another 5 or a third 5, a third score, it wouldn't change the mean because it is right on the balance point of the mean. All right. So that is why if you add or remove a score that's equal to the mean, the mean is not going to change. All right. So now let's talk about those constants. So let's say if I added a constant of 1 to each score. So my scores were 1, 2, and 3, but now I added a 1 to each score. So 1 plus 1 gives us 2, 2 plus 1 gives us 3, 3 plus 1 gives us 4, right? My mean originally was 2, but if I added a constant of 1, well, my mean is just going to change by that particular constant, right? So I don't even have to do the math. If I say, hey, we're going to add a constant of 1 to each of the scores, what is the new mean? The new mean is going to be whatever the constant added to the mean would be. Same thing if we did a subtraction, the same logic. So I should put here adding or subtracting. Okay, but now if we are multiplying or dividing by a constant, so let's say we multiplied each score by 2. So that's our constant. So our scores were 1, 2, and 3. But now it's 1 times 2 gives us 2. 2 times 2 gives us 4. 3 times 2 gives us 6. So these are the new scores. If we calculate the mean is now 2 times the original mean. 2 times 2 is 4. All right. So that kind of illustrates the properties of the mean and how they change if you add or subtract or multiply or divide by a constant, or if you remove a score or add a score. All right, let's continue. So here's a practice problem, right? We begin with a sample of 5, right? 5 scores. So it's a sample size of 5. And the sum of the scores is 35. And the sample mean is 7. So let's say if one score with a value of x equals 11 is removed from the sample, what is the mean for the remaining scores? All right, the answer is 6, but we're going to show how you get to that, right? So this will take some work, but bear with me, right? So the sum of scores equals 35, right? The sample size, number of scores is 5, and the sample mean equals 7, right? We are going to remove a score of 11, right, from the sample. So right here, if we remove the score of 11, well, the sum of scores have changed. Now it's going to be 35 minus 11, right? Which would give us a new sum of the scores was going to be 24, right? So 24 is the new sum of all the x scores. But it's also, if we remove the score, right, it's also going to change the sample size, right? The sample size was 5, meaning that there's 5 scores. Well, now there's one less score. So it's 5 minus 1. And so that's going to give us a sample size now of 4, right? And so now, if we just take 24 and divide by 4, which is the number of scores in our sample, it is going to give us a sample mean of 6. And that's how you would handle that particular problem. All right. Give me a second, just erasing this stuff right here. Okay. Give me 1 second, y'all. All right. So I also want to stress that the mean is highly sensitive to changes in scores, right? Let's say we had a distribution of 5 scores. So one person scored a 3, 2 people scored a 6, one person scored a 9, and one person scored an 11. If we're looking at the mean as a balance point, right? So let's say if we add up all those and divide by 5, the sample size, we get a population mean of 7, right? If we were to add a score, right, that was really, really, really large, right? So somebody got a score of 99, right? So if somebody got a score of 99, right, and this is a seesaw, right? Well, that is going to change the mean dramatically, and the mean is going to go further and further to the right in order to balance the scores that we have. All right. And so the mean is going to get really, really large. All right. And so what I'm trying to stress that the mean is highly sensitive to changes in scores, especially if we add a very, very large score. And it's one that we're going to go over when it's appropriate to use the mean or other measures of central tendency. And one of the inappropriate times to use a mean is when we have a score that is far and away radically larger or bigger than all the other scores in our sample or in our population of scores. All right. All right, so let's go to another learning check. So this time we have a sample of sample size of 7 scores, and the sample mean is 5. If all of these scores are doubled, what is the new mean? Well, if all the scores are doubled, then that means it is a constant, right? It's a constant of, you know, times 2, right? It's a constant of times 2. And what have we learned? That if you apply a constant to all the scores, then the mean is going to change by that same constant, right? So if all the scores are double, then the mean is also double, right? 5, times 2 or 5 plus 5 would give us 10, all right? So that would be the answer. The answer would be 10, all right? So that was for the mean. It's our first measure of central tendency. We're going to move on to the median. Now, if you remember in grade school when you learned the median is the middle, right? Median middle. And so the median is the midpoint of the scores in a distribution when they're, this is very important when they're listed in order from smallest to largest. That's very important. And so the median divides the scores into 2 groups of equal size. So the median is a 50% line, right? It's going to divide it into 2 equal sizes, our population or our sample size of scores. Let's look at an example of this. So if we have an odd number of scores, right, this is relatively easy, right? You're going to put the scores in order from least to greatest, right? And you're going to identify the middle score to find the median. Now, like we did in grade school, the best way to do this is to systematically cross out scores once you've arranged them from smallest to largest. So 3, you cross that out, and then you cross out 1 from the other side, 11, and you cross out another from this side, and you cross out another from the opposite side until you get to the middle score. That's if we have an odd number of scores. So the middle score, right, in this instance, is the median. Median is going to be 8 in this particular example. All right. But it's not always so easy, right? So if we have an even number of scores in either our population or our sample, we're still going to put the scores in order, all right? And then what we're going to do the same kind of crossing out of scores until we find the 2 scores that are in the middle. And then we're going to take those 2 scores and find the average, the arithmetic mean, right? So in this one, we're crossing out the lowest score, crossing out the highest score. Then we're crossing out the next lowest score, then the next highest score. And so right now, we're left with 2 scores that represent the middle. So we're going to average those out. 4 plus 5 divided by 2, it gives us 4.5. 4.5. All right, so that's going to be our median for this particular data set. All right, so the median, what's the relationship between the median and the mean and middle, right? So again, the mean is the balance point of a distribution, and it's defined by distances. This is very important. It's defined by distances, the distance that the scores are from the mean, all right? But most of the time, often, all right, it is not going to be the middle point of the scores, all right? A lot of times the mean isn't even a score isn't even one of the scores in the population of scores, right? However, the median, right, is the midpoint of the distribution. And it's defined by the number of scores. But it is not the balance point of the scores, like the mean is. And so again, what I want to stress is that both of these measures are measuring central tendency using two different conceptualizations of middle. All right, so let's look at some problems. All right. So in this one, it's asking us, what is the median for the following set of scores? Right? Well, they're already arranged. The scores are already arranged from smallest to largest, going from left to right. So then we just cross it out. So we cross out the lowest score, cross out the highest score, right? And that leaves us with two scores of 6 and 8. So if we add 6 plus 8, right, that's going to give us what 14. And if we take 14 divided by 2, it's going to give us 7, right? So our answer for this question is 7. All right, the next question asks, what is the median for the sample presented in the following frequency distribution table? So what is the middle point, right? So this one, the best way that I would go about doing this is to list out the scores from least to greatest, right? And so we know there's 3 people who received a score of 1. So it's 1, 1, and 1. There's 2 people who scored a 2. So that's 2, 2. There's 2 people who scored a 3. So that's 3, 3. And there's 1 person who scored a 4. Right? So now they are arranged from lowest to highest. And all we have to do is cross out scores until we find the middle point, right? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. So we know already that we're going to have to average something because we have an even number of scores, right? So we have 1 is the lowest score. Then we cross out the highest score. Then we cross out the second highest score. All right, and we keep doing that. So now we're left with 2 scores of 2. All right, so if we average those out, 2 plus 2 is 4. 4 divided by 2 gives us 2. So the answer is going to be B. All right, so the third question, it has to deal with giving a continuous measurement or precise median for a continuous variable. We're not going to do that in this class, but so you won't be responsible for that. And neither will you have to do that on the homework either. All right. So don't worry about questions of that type. Or if you want to, you can read about it and learn about doing it that way as well. All right. So let's get rid of all that stuff. Okay. So here's another question. All right. Decide if each of the following statements are true or if they are false. The first one asks, true or false? Is it possible for more than 50% of scores in a distribution to have values above the mean? Well, that is going to be true, right? More than 50% of the scores in a negatively skewed distribution are going to be above the mean, right? So that is true. The second question asks, true or false? Is it possible for more than 50% of the scores in a distribution to have values above the median. Well, that's going to be false because the median identifies the middle point of the distribution, right? The 50% of it is going to be higher and 50% is going to be lower than that median, right? So you can't have 60% of scores above the median, all right, or 80% of scores above the median. It's always kind of 50-50, all right, above, below. And here are the answers, all right. Okay, so the last measure of central tendency is the mode. And if you remember from grade school, the mode means the most, right? So the mode is going to be the score or category that has the greatest frequency of any score in the frequency distribution. And the mode is really flexible. It can be used with any scale of measurement. And it's always going to correspond to an actual score in the data. It's also possible that you could have more than one mode. Here's an example of when you have more than one mode. So this is called a bimodal distribution, right? These are students' achievement scores, right? We have one mode, which is really high, right, of students who scored a 17, right? 6 people scored 17. And we have another high one where 7 of our participants scored a 22. So this is a bimodal distribution, bi meaning two, modal meaning mode. So there's 2 modes, all right? Now, normally when you see this in research, more normally you won't see this in research, first of all. And the reason is, if you find yourself having 2 modes, that means that you probably have 2 different populations that are being presented in the same graph. And so what you would want to do, and what most researchers would do, is they're going to separate the 2 populations to create 2 separate graphs, all right, instead of keeping it with this bimodal distribution, all right? But that's just an example of when you could have more than one mode. Okay. So let's do some questions with the mode, all right? So for the sample shown in the frequency distribution table, what is the mode? So what score, which score comes up the most, right? So one person scored a 5, four people scored a 4, 3 people scored a 3, 4 people scored a 2, and 5 people scored a 1. Well, 5 is the largest. Sorry. Yeah, so 5 is the largest, right? The majority of people scored a 1, right? So 1 is the mode. Don't mess up and say 5 is the mode, because it's not. 1 is the mode, because 1 is it's the actual score, all right? All right, so the answer for that is D, 1. All right. So we're going to skip this question, right? For the third question, what is the mode for the following set of 8, of a sample size of 8 scores, right? So they're all arranged from least to greatest, right? You got 2, 4, 4, 5, 7, 8, 8, and 8. Well, the score that comes up the most is 8, right? Because they have 3. 1, 2, 3. All right. So the answer is going to be D. All right. Now you might be saying to yourself, well, this is very, very simple. I kind of learned this in high school and in middle school. I assure you, it's going to get more complicated. Make sure you have a good foundation with this part, before it gets more complicated. All right. Let's see. All right, so now we're going to talk about central tendency and the shape of the distribution, right? So, like we talked about last class, we could have what's called symmetrical distributions. And in a symmetrical distribution, the mean and the median are going to have the same value, all right? And if there is one mode, it too is going to have the same value as the mean and the median. So if it's one mode and it's a symmetrical distribution, the mean, the median, and the mode will all be the same number. If a distribution could have more than one mode, or it could have no mode at all. And so let's look at some examples of that. So this is a symmetrical distribution, right? In fact, all three are symmetrical distributions. In this one, this is the normal curve, or the bell curve, the normal population distribution, also known as a Gaussian distribution. In a Gaussian distribution, the mean, the median, and the mode all have the same value, all right? Like I said, if the mean and the median, if it's a symmetrical distribution, the mean and the median are going to have the same number. If it's only one mode, which there is, there's only one mode, then that too is going to be the same number as the median, the middle number, and the mean, which is the balance point, all right? In talking about the distance of each score from the mean. But this too is a symmetrical distribution, B, right? In this one, the mean and the median are going to be the same number, right? So the median number is right in the middle, and the mean is the balance point between these two halves, all right? However, that has two modes. One mode's here, and another mode is here, all right? But that is a symmetrical distribution, all right? We could also have no mode, right? No mode. So if it's a symmetrical distribution like this one is, because you could cut this in half and fold it on each other, and it's a mirror, right? The mean and the median are still, if it's symmetrical, the mean and the median are still going to be the same value, but it has no mode, right? If this is the y-axis is talking about the frequencies, right? Each score in this 1, 2, 3, 4, 5 has the same frequency. So let's say this is 1, let's say this is 2, let's say this is 4. So each score has the same frequency. If they all have the same frequency, then there really isn't a mode to talk about. So there's no mode in this particular symmetrical distribution. All right. So some ways of kind of figuring out what's going on when we have skewed distributions. All right. So like I said earlier, a couple of slides ago, the mean is influenced by extreme scores. All right. And it's found far toward the long tail. All right. Whether the tail is in the positive direction or negative, right? The median, right, in order to divide scores in half is found towards the long tail, but not as far as the mean. And the mode is going to be found near the short tail. All right. So if the mean, if you subtract the median from the mean and it is greater than 0, the distribution is positively skewed. But if you subtract the median from the mean and it is less than 0, the distribution is negatively skewed. So let's look at some examples of this to get a better picture of it. Give me a second. Okay, so this is a negatively skewed curve. We know it's a negatively skewed distribution because it has a long tail, right? A long tail facing the left. This is a positively skewed distribution because it has a long tail, right? Long tail facing the right. And so in these skewed distributions, we know where the mean, the median, and the mode are going to lie. All right. The mode in a negatively skewed distribution is going to be the furthest away from the tail. That's because most of the scores are going to be right here. So that's where the mode is going to be. And the mean is going to be closest to the tail because the mean is very sensitive to extreme scores. And these scores right here are very extreme. So it's going to make the mean closer to those particular scores. And the median is going to be in the middle between the mean and the mode. All right, so that's for a negatively skewed distribution. For a normal distribution, right, again, the mean, the median, the mode, if it only has one mode, is all going to be the same number, same value, right? Now, if we have a positively skewed curve, right, positively skewed distribution, the mode is going to be where the majority of scores are, where the majority of scores are going to be far away from this particular tail. So it'll be on the totally the other side. That's where most of the scores are, right? Because this is again a relative frequency, right? So the frequency is going up, right? So a lot more people have this score than who have this score. The mean, again, because the mean is very sensitive to extreme scores, which those scores in the tail are very extreme, the mean is going to be pulled closer to the tail. All right. And the median is going to be in the middle of the mode and the mean, right? And so that is how that would look for those particular kinds of distributions. Okay. Let's see. Let's skip this one. All right. So in this question, the distribution of scores shows a mean of 31 and a median of 43. The distribution is probably negatively skewed, right? So we have a distribution, right? The mean is 31, right? And the median is 43, right? If we look back, right? Right? If we look back, the mode is going to be on the other side of that, right? So this would make this distribution negatively skewed. All right. So now we know a little bit more about measures of central tendency. However, when you're doing a study, it's very important that you know when to use which kind of measure of central tendency. What is the best one for the particular type of data that you have? So if we want to know when is it appropriate to use the mean? Well, if you can calculate the sum of scores, right? If you can calculate the sum of scores, then it is appropriate to use the mean. All right. And it's also appropriate if you know the value of every score. If you don't know the value of every score, it is not appropriate to use the mean. All right. The mean could be misleading, and you'll see this a lot when you read advertisements and statistics by the news media. You'll see them using statistics in an incorrect way. It measures essential tendency. So it is not a good idea to use the mean if you have extreme scores, right? So again, if these if you have 4 scores, right, in your population, 1, 2, 3, and 1,000, right? Well, that 1,000 is a very extreme score, and it is going to make the mean very, very, very high. But not only is it making it very, very, very high, it's not accurately telling you where the center is, because most of the other scores are close to each other and way smaller than this extreme value. So that is why it is not a good idea to use the mean if you have an extreme score. For the same reasons, it's not a good idea to use a mean if you have a skewed distribution, right? Because again, you have some extreme scores. It's also misleading, right, to use the mean if you have undetermined values, right? So let me give you an example. Let's say we have a study where kids are doing a puzzle and we're timing the number of errors or the amount of time it takes to complete the task. Let's say we have 4 children, right? 3 of the children finish, right? Finish the task and they're given a time. But one student, one child never completes the puzzle. So there's no time to jot down. So you don't have a score. If you don't have a score for that 4th child, well, you can't calculate the sum of those scores, which is a part of the formula for calculating the mean. So undetermined values, it would be misleading if you just took the values for the time for the other 3 students, the other 3 children, right? Because you're missing one other person, right? So that's not a good idea. And it could be misleading to use the mean in that kind of scenario. Another, it could be misleading to use the mean is if you have an open-ended distribution. So what do I mean by that? So let's say I am counting, right, how many, I have a study where I'm counting how many pizzas each child ate, right? And so I give scores to each of the students and how much pizza they ate. But the one person, they ate way more than all the other students in pizza. And instead of giving them a score, I just said, hey, they ate 5 or more pizzas, right? Well, what is 5 or more pizzas? That could be 6, that could be 10, that could be 100. That is an open-ended distribution. Is that a real number that we could use, again, to calculate the sum of the scores? All right. So we can't use it there. All right. Also, like we talked about in chapter 1, we can't really use the mean. It'd be misleading to use the mean if we have an ordinal scale or a nominal scale. Because remember, these are just categories and you don't have any numerical values to calculate, right? So how are you going to calculate the mean for eye color or the mean for, ethnicity? You can't, right? Because those aren't numerical scores. Those are just categories. Those are just categories. All right. So it's a good idea, it's appropriate to use the median, right? If you do have extreme scores, right? So let's go back to my example that I was using, right? Let's say our sample size or number of scores is 1, 2, 3, 4, and 1,000. Well, now, if we're looking for the median, we're using that as a central tendency. Well, it's not affected. It's not affected by this extreme score because the median here is going to be 1, 1,000, 2, 4. So the median is going to be 3, right? And 3, is a better, is a more appropriate central tendency measure in this particular instance, right? Because most of the scores are very close to that particular number, and it's not influenced by this extreme score of 1,000. So it's good for when you have extreme scores. It's also good for the same reasons when you have a skewed distribution, right? Because the skewedness is because there are some scores that are very, very different from the bulk of scores. All right. It's also good when you have undetermined values. So in the example I said with the kid trying to complete the task and being timed. Well, now if I don't have a time for that particular child, right, that won't affect the median because the median is just going to be the middle of the distribution. So even if I put a number, let's give that child a really high number. Well, the median is still going to be the middle of the scores. All right, so it's not affected by that undetermined value. It's also better to use a median, right, when you have an open-ended distribution. So in the example I talked about with the counting how many pizzas the children ate, if one child, we gave them the category where they ate way more pizzas, and we said, hey, this kid ate 5 or more pizzas. Well, that's open-ended, but again, it wouldn't affect the median because the median is looking for the 50% mark, which separates one side of the distribution from the other. All right. It's also it's appropriate to use the median if you have an ordinal scale. All right. Because you're just using categories, right? And the ordinal scale ranks, right? You can use the ordinal scale to get a median, but it's going to be misleading, right? To try and get a median for a nominal scale, because those again are just categories, right? You can't. If I have a study where I'm categorizing the majors that people are taking at Bethune-Cookman. So I have one person who's a psychology major, another person who is a chemistry major. What is the middle of that? What is the midpoint of that? There is no midpoint. All right, these aren't quantitative values. They're categories, right? Which is essentially the nominal scale. All right. So it'd be misleading to use the median in that sense. All right. So the mode is the last measure of central tendency. And it's appropriate to use the mode if you have nominal scales, because the mode is the most, right? So if we go back to the example of the majors, right? This time I'm just counting what is the most frequent major chosen by Bethune-Cookman students, right? So I could use I could have a nominal scale. If I have a nominal scale, I could use the mode. That'd be appropriate. It's also for the similar reasons. If you have discrete variables, right? So if I have an assessment that categorizes people into different personality types, A, B, and C. If that's a discrete variable, and I'm just counting how many people have that particular are in that particular category, right, of personality types. The mode is also appropriate to use if we're going to describe the shape of the distribution, right? The mode is not a good measure if, or could be misleading if we're using it with interval or ratio data, except to just accompany the mean or the median. All right, it's better to use the mean if you have interval or ratio data. I didn't kind of describe why this is the case. Well, so why is it appropriate to use the mode for describing shape? Well, because the mode is going to give you the idea of where the peak of the distribution is. If we go back to a distribution, right, the mode is telling you where this peak is, right, in the distribution, right? What is the most frequent? So that can give you a good idea of what the distribution looks like. All right. All right, so we could also illustrate means or medians in a line graph. All right, so in this one, we have, in the x-axis, we have drug dose, and on the y-axis, we have mean food consumption. All right. So we're talking about the means when you have a drug dose of 0, 1, 2, 3, and 4. All right. So if you have a drug dose of 0, the mean was 20. So that's where our dot goes. If you have a drug dose of 1, the mean is a little bit higher, around 21. If you have a drug dose of 2, the mean is 15. If you have a drug dose of 3, the mean is about 5. And if you have a drug dose of 4, the mean is 10. Right? Because drug dose is a continuous variable, a continuous line, right, is going to connect the dots at the different levels of dosage. All right. Here is a bar graph illustrating the means and the medians for homes in different regions of the United States. We have Northeast, South, Midwest, West. All right, we know this is a bar graph because these are separate, right? These are discrete variables, right? You can't be in the Northeast and the South. You can't be in the West and the Midwest. All right, you're in either one category or the other. All right, and they're separate from each other. Right, and so this one is saying, hey, median new houses, right, in the Northeast, their mean, right, the median cost, right, in the thousands is about 115,000, somewhere in the middle here. All right, for those homes in the West, the median new house cost is about 125,000. All right, that's how you would interpret the means and the medians in a bar graph. All right. All right, so let's do some of these questions. So a researcher is measuring a problem-solving times for a sample of 20 laboratory rats. However, one of the rats fails to solve the problem, so the researcher has an undetermined score. what is the best measure of central tendency for these data? Well, we know if you have an undetermined score, well, you can't calculate the sum of the scores, which is a part of calculating the mean. So it's not going to be the mean. You could use the mode, but it's not the best measure. The best measure would be the median, right? Because it tells you the midpoint in the data, and it's not subject to be influenced by those extreme scores or undetermined scores. So it's going to be B. Number 2, what is the best measure of central tendency for an extremely skewed distribution of scores, right? So that too is going to be the median for those same reasons I outlined for the first question. Third question is, one item on a questionnaire asks students to identify their preferred animal for the school mascot from 3 different choices. What is the best measure of central tendency for the data for this question, right? So this is asking the preferred animal, right? For the school mascot. So these are just categories, right? They're just categories, and the categories aren't ranked at all, right? So that means we're dealing with a nominal scale of measurement, and these are discrete variables. All right, your preferred animal can't be 2 options, it's just one option or the other, right? So if we're using a nominal scale, right, the best measure central tendency to use is going to be the mode. All right, best one's going to be the mode. All right, and so here are the answers to the questions. All right, here are some additional questions, right? So we want to decide if each of the following statements are true or false. So this one says the mean uses all of the scores in the data, so it is the best measure of central tendency for skewed data. Well, we already know, we just went over this, that if you have skewed data, all right, or extreme scores, the mean is not the best measure of central tendency to use because it is highly influenced by extreme scores, all right, and skewed data. So that would be false. The second question asks, true or false? If the mean and median have the same values, the distribution is probably symmetrical. Well, yes, right? If the mean and median are the same score, the distribution has to be symmetrical, all right? It has to be symmetrical, balanced 50% above and 50% below, all right? And so here are the answers to these questions. And so that brings us to the end of the 3rd chapter. Once again, I thank you for listening to this lecture. I hope you learned a lot. If you have any questions or concerns, please do not hesitate, again, like I said earlier in the lecture, to contact me, and we can go over this in more detail. All right, I'm in the nursing building, room 205, or you could just hit me up on Canvas or my email at floodm@cookman.edu. I thank you for your time, and you have a great day.